force very briefly when we were doing Kepler's laws, but this is something that's going to come up again and again, but not in a big way. So I just want to go over it one more time very quickly, such that I don't forget about it. So gravitational force between any two masses, F, let's say there's a mass M1 and there's some other mass M2. It doesn't matter how big or small these masses are. Gravitational forces are exerted for electrons as well, although that's a very, very big force. And the primary force when you're talking about electrons would be electromagnetic repulsion. And that's Lorentz force. But gravitational force basically says that the amount of the force, the magnitude of the force would be a universal constant G, M1 and 2, so the product of the two masses, divided by r squared, where r is the distance between the two masses. So if this is r, then that is the definition of the gravitational force, and you should be as comfortable as possible with it. Now, gravitational force is always attractive, right? Gravity always attracts. Gravity never repels. So in that way, gravity is very different from other forces, because other forces can be attractive or repulsive. Not always, but a great deal of them are. So G is a universal constant. A universal constant basically means no matter where in the universe you might be in some other galaxy, but you'll be able to measure the same G. So the constant G is a constant G that's the same across the universe. The other thing also is that this power is precisely 2. It's a 1 over r square law. Inverse, these are called inverse square laws, force laws. So the way this works is that M1 will actually attract M2. So M2 will feel a tug towards M1. That will be that way. So this is what M2 feels. And M1 will feel a tug towards M2. That's what M1 does. They're attractive forces. I just wanted to remind you about gravitation forces. So that's one thing I wanted to mention. Now, gravitational forces come in a very big way because you may consider, for example, moon going around the Earth, or Earth going around the sun. And these orbits, as we know, are elliptical orbits. They are not circular orbits in reality. But circle is a simplification of an ellipse. An ellipse basically is a flattened circle. So, as we discussed last time, the major axis of the ellipse and the minor axis of the ellipse, because the flattened circle, are different. But if the two were equal, then the circle converts itself the ellipse converts itself to a circle. So normally what we have done is we have taken circular orbits to simplify our lives, and then we have related that to circular motion because we know if something goes around in a circle, there is a centripetal force. So if let's say moon is going around the Earth in a circular orbit, there is a centripetal force. The distance between the Earth and the moon is something, let's say some r. Then it's mv squared by r, m being the mass of the central object in this case. So it's going around, and that can be equated to the gravitational force and so on. So this is typically how we use these problems. I might throw in a few of these homework problems and some quiz problems around this, just so that you're on top of it. But I just wanted you to not forget about it. All right. So that's one thing. The second topic that I wanted to cover, actually I have covered, I want to remind you, is the all-important work energy theorem. Work energy theorem was already covered in exam 2, but I just want to emphasize how important it is and what it leads up to. Because work energy theorem has important consequences. You guys are bothering me, all four of you. Yeah, don't look the other way. It's 1, 2, 3, 4. So just take a chill pill. Calm down. I hear any more conversation, all four of you will be barred from today's quiz. Alright, so the work energy theorem basically says something very simple, that if let's say if I go from A to B, and I do some work in that, so work, as we know, is the dot product of force and displacement. So let's say in this case the displacement here is d, I can make it into a vector. I'm going from A to B, so I can make it A to B. Then this work done is the kinetic energy at the final point. So that will be 1/2 mvv squared minus 1/2 mva squared. Okay? So work energy theorem basically means that the work done in going from A to B is the difference between kinetic energy at this point minus the kinetic energy at the initial point. So when you look at it, it may not sound like a big deal, but this theorem, as I mentioned before, is indeed a big deal. Why? Well, it is a big deal because there is no specification of what kind of force might be involved, right? So this can be a natural force, simple force like gravitational force. This can be a spring force. This can be a force that is well, all forces are natural, so that's probably not the right word. But this can be a very basic, fundamental kind of a force. Or it can be an extremely complex force. For example, frictional forces. As we discussed, frictional forces arise because of surface roughness at the atomic scale, right? So frictional forces therefore have a very complex origin, and this force can also be a frictional force. So therefore, this theorem, the work energy theorem, allows us to calculate the effects of distributive, like frictional forces, as well as non-distributive, simple forces that nature typically gives us. For example, gravitational force, electromagnetic force, spring force, and so on. And we'll cover some of them today. It also has an interesting consequence because it leads us to something that we call energy conservation. Now, energy conservation is a very simple idea. The idea of energy conservation is that the idea of energy conservation is that the total energy of the universe is fixed. So in other words, there is no new energy suddenly ending up in the universe or going away from the universe. Now, what it boils down to in a very realistic way is that the total amount of energy in a system, which is a closed system, things are not running out of it, is fixed. So let's say there is no air that can flow in and out of this room. Let's say the doors are airtight. Of course, nothing in reality is completely airtight. But assume that's the case. What that boils down to saying is that the total energy in this room, which is the energy of all the gas molecules, energy in each of us, blah, 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 that is fixed. Okay? So energy conservation, therefore, may seem like an obvious, simple thing, but it has extremely important consequences in terms of our ability to learn about the forces and so on and so forth. So therefore, we want to learn about energy conservation, how that connects to the work energy theory. Any questions so far? Okay. So let's do a simple experiment, thought experiment. I have two levels, let's say A and B. Okay, so let's say A is what I call the higher level, B is what I call the lower level. And this can be something as simple. For example, the top of the table here can be your A, and the ground level there can be your B. So imagine something as simple as that. So suppose I have a mass here, little ball at the top of the table. And of course, if I let this ball go, I know what's going to happen. Gravity is going to put it down. The downward force here would be the force due to gravity, which we will capture on Earth as m times g, right? G being the acceleration due to gravity. So it is very easy now to calculate the work done as I go from A to B in this case. Let's say this height is h. Let's keep life simple. I just say that the work done from A to B is the force mg. I'm not going to put in vector notation and so on and so forth. Mg is downward. And I'm also headed downward, right? So therefore the displacement is also downward, which means mg and h are in the same direction. So that means you have mg times h times cosine of what? 0. And cosine of 0 is what? 1. Cosine of 0 is not 0. So therefore this is mgh. right? So this is the work done as you go from A to B. And I can also therefore say by work energy theorem that this should be 1/2 m VB squared minus 1/2 m VA squared. Any objections to that? Is that okay? Or is it problematic? Well, I've done something that is somewhat illegal. You should suspect everything I do. That's your job. You shouldn't believe me. If you believe everyone, then you are very gullible. Right? Do you want to be labeled gullible? Only a few just shook their head. Most people are quite okay with being gullible. Alright. So I can rewrite this. I can basically write MGH, let's say, as mg times upper level, in this case YA, minus mg times YB, where YA is the height of this point and YB is the height of this point, lower. So this is my YA. That's implicitly what I'm saying. And this is my YB. Is that okay? Cool? No? Don't be so silly on me. Come on. I also didn't sleep last night.
Why is not YB minus YA?
What?
Why is not YB minus YA?
Why? Because I can just take two levels, right? I can call this level YA, I can call this level YB. So I can write H as a difference between the two levels. It's as simple as that. Yes?
So the 1/2 MVB squared minus 1/2 MVA squared is interchangeable?
Wait a minute, I didn't say that. Final minus initial is important. It has to be final kinetic energy minus initial kinetic energy. The final is B, right? I went from A to B. I didn't go from B to A. Yes? All the stupid heads out there, is that okay? Alright. So I will do something which is, I will now write this. Y work energy theorem is 1/2 mVB squared minus 1/2 mVA squared. Okay? So now you see what happens. Is that okay? Am I pulling something? Faster? Are you sure? If I try to... Alright, let me just finish this up. So let me now say, work energy theorem has gotten me here, and now I would say this implies, this means it implies, that if I pull the 1/2 mVA squared to the left, the minus sign flips into a plus, so I have a 1/2 mVA squared, right, plus mgYA. Suppose on the left hand side I collect these two guys, and I banish to the right hand side all the B terms, so that will be 1/2 mVB squared, and then this one, which had a minus sign, now flips into a plus sign because it has been banished rightward, so that would be mg times YB. Whenever you have a relationship where the left side equals a right side, this equation, in this case, is telling you that whatever is going on this side, obviously, is whatever is going on the right side. They are the same things. Of course, the difference is, in one case, everything is going on with regard to point A, which is on top. And in the second case, everything is going on with regard to point B, which is at the bottom. And you already know, what is this? Kinetic energy. So kinetic energy at point A should be high or low? Only one person is responding. Why should we have already heard it from him? But kinetic energy at A should be low. Why? Why? Yes.
Because it hasn't moved as much as B.
So basically you're dropping it. Correct. That's the reason. So obviously as it goes down, it will speed up, right? It doesn't happen the other way. So when you drop something, it speeds up. That's what our experience in education tells us. So the kinetic energy at A, right, is less, and the kinetic energy at B is more because it has come down, it has fallen. You're already being told that the left side is equal to the right side, so that must mean if this is less, then this is high in this case, and that is low, right? Otherwise, the two won't balance, isn't it? So what is going on here then? What is going on here is that I'm telling you that when I'm dropping the ball, when I'm dropping this mass, the kinetic energy here is low, let's say, or 0. And this term is high because of h. And what's happening on that side, the kinetic energy here is high because it is falling. It is falling to this point, but mg yb must be low, otherwise the two cannot be equal, right? Yes, so that part of it is what will, so therefore there are two pieces to the energy equation. This is basically an energy equation. In fact, this equation is an example of what we call conservation of energy in this case. Okay? Not for the entire universe, but the conservation of energy for this mass. Now there are two kinds of energies that's involved here. First is that you have kinetic energy, which is energy by virtue of motion. Motion, why? Because there is velocity involved. So this is kinetic energy. This term is kinetic energy. That's why I call it kinetic energy at A and B. But this term here is energy by virtue of position. That's what we call potential energy. So kinetic energy and potential energy are two important pieces of total energy that would typically enter into these equations at this level. That doesn't mean that it takes care of every possible energy. Actually, it doesn't. But at the simplest level, with the kind of stuff we are dealing with, this equation is adequate to tell you what is the total energy of the system. You've got to account for kinetic energy and potential energy. So in other words, if I climb on top of the table, will my potential energy change or not? It should, right? Because I am at a higher level. So do you guys sitting up in the gallery have higher potential energy or not? Let's take a vote. How many of you think you have higher potential because you are sitting at it? How many of you don't? You don't know. You don't understand why. Why? What is your potential energy? No, the girl behind you. I don't know. What is your potential energy? What is your mass, roughly? How many kilograms are you? You haven't been measuring yourself lately? You're lucky. I have to measure myself all the time because I eat some pizza and I put on weight. But all right, so it's a fact actually. I had pizza last night because I was feeling so greedy. And anyway, let's say your mass is 50 kilograms. We're going to talk in kilograms. Let's say it's 50 kilograms. What is the acceleration due to gravity? Come on, you should know this. Otherwise, you shouldn't be in this class. What is G? Huh? Speak louder. Okay, 9.801. Good. So you got M, you got G. What is the approximate height that you are sitting in with regard to the ground level? Just estimate. Height from here. So you are, how many steps are? 1, 2, 3, 4, 5 steps. Suppose each step is you figure it out. I'm asking you the question. Well, let's say for argument's sake you are 6 foot up. Right? So that's what, 1.8 meters. So your potential energy now you calculate. Write down on a piece of paper. What is mass times G times H? Calculate it. Consider G to be 10. So you see, if you don't answer me, I'm going to torture you like this. So your mass is 50 kilograms, your G is 10, and your height is 1.8. You can make it 2, just for the sake of simplicity. So what's your MGH? Come on, you don't need to write for that long. 50 times 10 times 2. Yeah, 1,000 what? See, all those details are popping out when you ask each other questions. 1,000 kilometers, 1,000 feet, 1,000 kilograms. If you yawn, I'm going to punish you. Loud, loud. I can't hear molecules moving. Yes, tell me. Okay. So basically that is a name. What is the name? Joules. So your energy, your potential energy is 1,000 joules. So suppose now the gallery collapses. God forbid. You will be hurt, but that's another matter. The gallery collapses and you will be ending up on the floor. So your kinetic energy will be half m VB, which would be the floor level in this case, squared, right? So while I do the lecture, I'll ask you what is your VB. You calculate that right now. Use work energy theorem, half m VB squared. You are sitting there, right? Do you have any kinetic energy? You have kinetic energy? Yeah, okay. So you don't have any kinetic energy, right? So you now fall, God forbid. So you fell and you landed on the floor. Yes? So what is your total kinetic energy when you land on the floor, and what's your velocity? That's the question. Compute it. I'm going to ask you in 2 minutes. Alright. So while I torture her, I'm going to then do something else. So in this case, what we did was we actually went down from A to B like this. Now suppose I don't want to go from A to B like that. Suppose I want to go from A to B like this. Except now I won't have quite the B anymore because B was here. Alright. I'll call this, let's say, I call this C. I know, so I'll call this C. Alright. Have you computed? Quick. No quiz if you don't compute. Quick. Half mVB. Okay, your kinetic energy on the ground level is equal to your potential energy now. Until I get the answer, I won't give you a quiz. So, you are not going to respond to the accurate torture. So this is a great way of getting you guys to engage. So suppose now this mass is coming down like this, and this is the mass, ball or block or whatever, it doesn't matter. The mg is downward, right? We have seen these line plates, and it's going this way, so let's say this is theta, which means this is going to be what? This force is going to be mg what? Along the incline. What? Why? Is it going to be cos theta? This is going to be cos theta. This is going to be sin theta. This mg sin theta is along the incline, right? Come on, this is something we did in so much detail very recently. Don't forget that. Spring rate should have that effect on it. So now you see, let's call this distance h. Okay? This distance here. Or maybe not. We already had h. Let's call this distance L, let's call this distance h. So, sine of theta would be what? Tell me. Sine of theta. What will it be?
H over L.
Okay. You are forgiven. You are correct. So therefore H is equal to L sine theta, right? Or L is H over sine theta. Is that okay? L is H over sine theta. So therefore I can write the work done in going from A to C as mg sine theta, which is my force, times L in this case, and that would be H over sine theta. Now something bizarre happens, you see. At this point what happens is that the sine thetas go away because theta is more than 0, which means that you end up with the same answer that you had when you took the other track, which was directly falling. So although you're coming down the incline, your work done is still mgh. How bizarre is that? And therefore by work energy theorem, this would mean 1/2 mvc squared minus 1/2 mva squared is going to be the kinetic energy difference, which would mean in this case that mg times ya plus 1/2 times m times va squared is mg times yc minus 1/2 m, plus 1/2 m vb squared. Or wait a minute, I have to include the record. No, let's call it vc squared. But then I already know that ya minus yc in this case comes out to be 8. So clearly there's something weird going on. Basically what's going on is that the potential energy at C is actually the same as potential energy at B. Otherwise these two cases don't compare, right? So this case here, basically when I'm coming directly downward, is giving me this equation, that equation, whereas this case here is basically giving me the same A to B as A to C as A to B. Therefore, for me to be able to respect everything, whether I end up at C or at B, it doesn't matter. How weird is that? So, is this correct? Did I make a mistake? You know, I'm very prone to making mistakes. I make mistakes all the time. But did I make a mistake? Look very carefully. Yes.
Are there any frictional forces?
Very good answer. Answer is no. Right? There are no frictional forces. And because there are no frictional forces, the detail of the path is unimportant, right? Because as it turns out, I have a coincidence where I have mg sine theta and h over sine theta cancel out. So in other words, I lose my dependence on L. And that will only happen, as he pointed out, because you don't have frictional forces. If you had frictional forces on the other hand, then the length of this path and the detail of this path would have mattered. But it turns out it doesn't matter because there are no frictional forces. So energy conservation here works out beautifully. In this case, it turns out that the energy at B or C or wherever it may be would be just the same. It only depends upon the level here, because that's really how mg in this case works. Mg is a downward force, and it doesn't matter how I go down from here to here, my difference will be the same. If I jump off and break a bone, it's still mgh, it's potential energy change that will happen. Here it's higher, here it's lower. If I go down an incline, it will be exactly the same, because as long as there are no dissipatory forces, I'm going to end up with this kind of situation. So therefore what we are seeing is that there is no path dependence because there are no dissipative forces, such as friction. Okay? So it doesn't matter how the path is. It will basically work out that your total energy conservation will work beautifully. Now this thing has an interesting consequence, and I want to take you there. Suppose now I go back to my original problem, and I start again, go down to B. Okay, so I let gravity take me down. So mg is downward, h is this. And since I'm going down, mg and the displacement direction are the same. So that's mgh. That's the work done. So work done in going from A to B is mgh. Now suppose I actually want to go back up. And to go back up, at fixed velocity, I apply an opposite direction force mg. Or I look at it the other way, I say that I'm going here to here, and if I go here to here, I have mg acting downward on me, and I have h, which is now in the opposite direction, so I put in a minus sign because the angle between the two is 180 degrees, so they are opposed. So it turns out then that the work done in going from A to B plus work done in going from B to A. If I add these two up, this is work done by whom? This is work done by mg. That's very important. This is equal to what? 0. So you see, when there is no energy loss, there is a very important consequence. Remember, we have lost our path dependence. The initial and final points matter. But whether I go down like this or whether I go down like that, it doesn't matter. That's what we showed with that inclined plane example. This is very serious stuff. What I'm doing for you is by no means simple to grasp, because this is not how our brain thinks. This is how nature works. So there is a path independence coming in. So in this case, I'm just going straight down, or whether I'm going this way, it doesn't matter. Because at the end of the day, the work done is mgh. It depends only on the final initial points. So in this case, work done by mg, because mg is always pointing down, is mg is acting that way, h first is downward. And the next case, the work done by mg is mg acting downward, h is upward, because I'm going from B to A. So therefore, the work done is minus mgh, because mg is this way, h is that way. And therefore, the net work done, so this is the net work done, if you will, as I went from A all the way back to A, is 0. So this is what happens when energy conservation holds. And these kind of forces, in this case, this mg is an example of what we would call a conservative force. So conservative forces are very important in nature, because as it turns out, all fundamental forces that nature gives us, not friction, which is a very complex composite force, but fundamental forces like Coulomb's law, which is how charges and attraction are done. Fundamental forces like gravitational law, which are looked up there. Fundamental forces like various forces inside the nucleus. These are actually all conservative forces. So nature only gives us typically conservative forces, and energy in the universe is conserved. Yeah.
So if instead of going back up to A, you went about halfway up towards A?
So then I will have some work done.
Okay.
Yeah. Then I will have some work done. So I can now extend this argument and say that according to conservative forces, if I go from, let's say, Rochester to Buffalo, or from Ithaca to Buffalo, or whatever, if I only have conservative forces at play and nothing else, then I can take whatever path I want, but as long as I return wherever I want to return, Buffalo or Rochester, my net work done, if I have conservative forces, let's say, just to remind myself, so in all conservative forces, a closed path journey gives me exactly 0 work done. How bizarre is that? But that's exactly how nature works. In this case, it turns out that basically you don't have any. Now, if you had dissipative forces, though, then it would be a very, very different story, because you will indeed be suffering from energy loss. Now let me move to another very important part of the problem, a set of problems that we're trying to do. I will not look at a fundamental force like I was looking at, but a very important force nonetheless. And this would be the spring force. And we will be spending a great deal of time on spring forces as we go along. So follow me very carefully, because none of the things here are simple as I said. So suppose I have some wall here, and I have some spring. Let's say, as before, we have talked about massless strings, right? Strings that are massless because that way they don't eat up the force they're conveying. In this case, we can think about the spring itself being massless with all its mass at one end. It's okay. It's a reasonable thing to assume. It's not real, but it's a reasonable simplification that doesn't cost us an arm and a leg. And typically, whenever you consider a spring, like a Slinky or whatever, a cheap spring that you can buy in any toy store, that spring has a spring constant. And this spring constant is usually denoted by the letter small k. So be very careful, do not write it to be big K. Big K is usually reserved for kinetic energy. So in physics, your notation is important. So normally, big K is something you reserve for kinetic energy. Use small k for spring constant. Otherwise, you might end up getting unnecessarily confused. So, the way this works, suppose now I pull the spring. So let's say I stretch the spring, and the spring goes here. So this is, let's say, x equal to x initial. I just call it x initial. So this is where the original end of the spring was. Now I have stretched it to some x phi. Okay. So if you stretch a spring, does the spring like to be stretched? Have you ever found a spring that there are springs that like to be stretched, but they're usually what we call pretty bad springs, right? It has lost its what? Elasticity. But elasticity is a very dicey word. I'll tell you a lot about elasticity soon, because elasticity is coming around as part of the syllabus. That's elasticity of materials, elasticity of this material, elasticity of my arm. Anyway, we won't talk about that part, but in this case we know that the spring will not like to be stretched if we stretch it. So therefore, to stretch the spring, I have to apply a force that way. And since this is my force and my initials are SS, I call it FSS. So I apply the force FSS and I stretch it by this distance here. So therefore, the work I have done, delta W, let's say, because it's a small amount of work, hence the delta. It's not anything mysterious. This would be my FSS, which is the amount of force I've applied, times, in this case, x final minus x initial. Well, let me just be very careful here, because I can write it that way, but I will just be a little bit careful here to keep my notation as simple as possible. Because I put a delta, let me just write delta x. So therefore, this is what I'm calling, for simplification right now, delta. Okay? So that's the work I have done. So if I now, okay, the first thing is, all right, this is a very important point. And a lot of people forget this, because since we are not giving a calculus-based treatment, it can be a little bit oversimplified the way I'm presenting it. So if I imagine you are stretching a spring. So when you start to stretch the spring, the resistance that the spring gives you is something. And then you have stretched quite a bit. So is the resistance force that you're getting from the spring the same or different? Not you guys. You have stretched it. And you stretched it more. So the question again is, as you keep stretching it, does the resistance force remain the same or increase or decrease? Increases. So more I stretch a spring, more the force is, right? Yes? Now this thing was originally observed by a guy called Hooke, H-O-O-K-E, and therefore this is called Hooke's law. So as you stretch a spring, the resistance force given by the spring, or the force you need to keep stretching it, goes up. And it goes up by the amount of the stretch. So that's the reason why I'm doing the spring, because that's the simplest situation that you can have. So in other words, what happens here is that your F in this case, okay, your F in this case is, or FSS in this case, would be equal to the spring constant K times the amount of stretch I have made. So that would be my delta X. So more I stretch, more is the force. So let me now plot this out. Because the force is not fixed anymore like we had for mg, right? When I drop something, it's mg. And the reason why we do mg in this class, in the very beginning, is actually quite simple, because the force is constant. And when the force is constant, it's very easy to get started and develop physics. But now we are taking a step forward, going beyond constant forces to a situation where the force can vary. So now if I plot my FSS, which is the force I am exerting, with the distance associated with the stretch, if I go, or you can call it delta x if you will, it doesn't matter. Then if there is no stretch, there is no force. But as I keep stretching it, my force goes up, and by Hooke's law, which is basically captured here, this force goes up like that. Okay? So therefore, let's say I take it at 2 points, x initial and x final. X initial can be 0, it doesn't matter. So then the force here would be F times, F equal to K. I can call it x1 and x2, let's make it simple. I can call it kx1 here, and the force here would be F equal, so that would be here, and the force here would be kx2. So I want you to appreciate the fact that force is changing, and that's very important, because this is where a lot of kids go wrong. This is the part that is tricky, this is the part that's important, this is the part that gets you down. So it's very important that you understand that as I stretch the spring, the force is increasing. So in other words, the force here, at this point, is kx1, because this is x1, here's the one stretch. The force here would be equals to kx2. And I have gone from, I've taken the edge of the spring from x1 to x2. So now how do we calculate the amount of work done? Because ultimately at the end of the day, I'm interested in using work energy theorem, so I've got to calculate the amount of work done. So, there are many ways of doing that. We will take the easier way because we are not doing calculus here. It's not necessary to do calculus. So therefore, this is my x-axis, and as I told you, this is my x1, and this is my x2, or x final, whatever I call it, x2. This is F equals kx1. And this is F equals kx2, and said force is going up. So this is my force axis, and this is my distance axis. So whenever you draw a plot, make sure you label the axes, give the arrows like I show you. The arrows show which is the positive direction in this case, increasing that way. So I want to get to the work done, since work done is force times distance, and it goes from here to here. I really have to end up calculating in this case, the area of this triangle, because that is the extra amount of work done in this case. I've taken it from kx1, where it already was. So it started at kx1. I've taken it to kx2 in this case, the force. So therefore, the shaded triangle there is the area that should give me the work done as I have done this way. So what I'm going to do is I compute the area of the triangle. And this can be done in a variety of ways, but one of the easier ways of doing it would be, let me just take the average force, because it increases smoothly. So I just take the average force. So if I take the average force would be kx1 plus kx2 divided by 2, because there are 2 points. So this is the average force involved. So that would be the force level associated with that dashed line that I have drawn. Okay? This is a very dangerous problem. That's why I'm telling you, I'm proceeding so cautiously. So this is my average force. Instead of doing the calculation of the triangle, what I'm trying to do is I'm trying to replace this triangle by this rectangle. Now, I don't want to calculate the triangle area. I just want to calculate the rectangle area by changing my varying force to a fixed average force, something we discussed at the very beginning of this class, and just get this area. So now you see it becoming very simple. So the work done, in this case, in going from 1 to 2, is going to be the average force, which is kx1 plus kx2 divided by 2, right? And then this distance, which is x2 minus x1. I want you to never forget this derivation, because the moment you forget this derivation, your chances of screwing up the formula involved in calculating the work done goes up 100%. Because you tend to memorize and you tend to get confused. And I've seen this over the last, you don't even want to know. So remember this derivation, remember this hat area, which is really what gives us, in this case, the formula for the work done. Okay, don't screw this up. Let me put it this way, if you screw it up, it will be double penalized. So now what happens is that I can take the k out, and I can take the 2 out. They're not making me trouble. So x1 plus x2, and then x2 minus x1. Yes? So let me just write it in a more beautiful way. Let me write it x2 plus x1 and x2 minus x1. What is that formula? A plus b times a minus b. So you can multiply it out if you want. But what you will find is that it will become k over 2 x2 squared minus x1. So the final point, the coordinate of the final point squared minus the coordinate of the initial point. It's not x2 minus x1 whole square. Don't screw it up. That's what's going to get you double jeopardy. Because these are double points. Or that kind of a terrible offense. That's like murder. Do not murder this formula. This is the right formula. This is how work done for a spring is calculated. It's 1/2 k. Don't forget the 1/2. The 1/2 comes from the fact that there's an averaging done. That's the origin of this 1/2. That's why you shouldn't forget this formula in college. So, so you can do a fair amount of calculations now, because we know that this is a conservative force actually, and the energy is conserved in this case. So it turns out that if I actually have a spring, and let's say I stretch it and let it go and so on and so forth, then I can set up a situation where I can say that this is my x initial, and then I stretch it to some arbitrary point, let's say A, and then I stretch it even more to some other point B, and so on. This remains x initial. Suppose you have a situation like this going on. It is very, very important for me to recognize that energy conservation, mechanical energy conservation, which is what we have covered right now, that is to say that kinetic and potential energy is conserved, implies that I should be able to write, let's say in this case, energy is equal to 1/2 the mass involved. Let's call this mass m. 1/2 mass times, V A squared, okay, plus 1/2 the spring has gone to A from x initial, so x A squared, that's the final point, so that's the formula, minus x initial squared. So that should be my kinetic energy. Sorry, that should be my potential energy at A. Likewise, if I want to compute the energy at B, and of course these two should be the same because energy is conserved. This is not a distributed force. Okay. So energy conservation comes out to be stated in a very particular way when you're dealing with springs. You've got to be very careful to be able to compute the potential energy of the spring. In this case, as you can see, the potential energy of the spring, because the spring has been taken from x initial or 1, whatever, to xA, this is the final position, that was the initial position. So therefore, the potential energy is the final position squared, x2 squared, minus x initial squared, minus x1 squared, okay? And same goes here. So I can put in the numbers and I can ask you to calculate. For example, I can say that, let's say x initial is 0. I can make up a problem. And let's say when x initial is 0, the mass is moving to the left. Left is negative, right is positive at minus 5 meters per second. I can make a problem like this. And let's say XA is 2 meters. I'm making up very simple numbers. M, let's say, is 1.0 kilogram. And the spring constant K, let's say, is 5.0 newtons per meter. Actually, spring constants tend to be fairly large numbers because most times we're dealing with rather stiff springs. So spring constant, a realistic spring constant may be 50,000 or more. But most systems that you consider. So in this case, for example, we can consider x initial. So x initial, as you can see, because x initial is 0, all energy is kinetic because the spring, the edge of the spring, the mass, is moving leftward at minus 5 meters per second squared. So per second, I'm sorry. So you can easily compute the total energy initially. So x initial is 0. I am just left with kinetic energy, 1/2 mv initial squared. And v initial is given as minus 5. Minus 5 squared is plus 25 meters squared per second squared. And if you m is 1, so therefore the number you're going to get is 12.5 joules. That's what you're going to get with a given set of numbers as my energy initially. Energy is conserved, so therefore we can ask the question that what is VA? And since energy is conserved, I should really write EA is 1/2 mVA squared plus 1/2 K XA squared. Because Xi is 0, I can write this. And if you carry through the calculation, you will find that you get a VA that is approximately 2.2 meters per second. So you can calculate that. XA is also given, so you know everything. So you can calculate. So that's a simple example of a spring problem. There is another case that turns out to be very important, and I just want to mention it, and I'll work it out in some detail. It's very simple actually, but it's a little scary to look at. I'll work it out in some detail on Thursday when we start the class. So here you see, you can be asked a problem like this, where you're coming down, you're skateboarding. So you're coming down from say level A to some level B, and then after you have reached the level B, you continue on this level B until you reach the point C. That's it. So clearly you can see that if you're starting from rest, this height would give you your potential energy, right? Because mgh. And here you see, if you know mgh by energy conservation, as long as you know m and g and h, in this case you can find out the kinetic energy, which is half mvv squared, because at this point you can call this the y equal to 0 level and call this the y equal to h. So you know the kinetic energy here, because by energy conservation that we did a little while ago, you can do that. Now let's say a very common problem that you'll be asked is, suppose from B to C, the path is frictionless. So if you're moving that way, friction force would be the other way. Right? So friction force would be like this. So friction is this way, you're moving that way, you're doing negative work. By work energy theorem, you can compute the amount of frictional force-based energy loss. And from that, you can calculate what this VC would be. So this is a very common problem, very simple problem actually. You just have to realize that you're using work energy theorem. This point energy is conserved because you're just coming down, there's no friction, nothing. But from this point to that point, there is friction, and so therefore you're slowing down, right? You're slowing down, and the work done by friction, this part, is simply going to be F friction, which is going to be that way times this distance, let's say x dc, which is this distance here. And because friction is that way, moving the other way is minus. That's work done. So whatever is the kinetic energy, so the total energy, let's say at A, is going to be your mgh, is equal to 1/2 m v squared. That's what's going to happen here. And the energy loss that you're going to have is going to be minus F friction in this case, or F, I call it small f, F friction times x dc. And so therefore, kinetic energy at C now would be the initial energy, which was all kinetic, so half mvv squared minus F friction x bc, only 1/2 m bc. So these are very common problems, and these are the kind of problems that I've been ramping up to and going a little bit beyond that, because this is really too simple at this level. So just work through this problem and make sure that you can do problems like this. All right, let's move to the quiz now. Get this started.